The next functional group that we're going to talk about is alkynes, and alkynes are, of course, the triple bonds. The nomenclature of alkynes is as straightforward as it can be for alkenes also. The suffix is going to be the "-ine", and if it's a simple alkyne, then you just start from wherever the alkyne branching is. So for example, in case of 2 carbons, which is the smallest alkyne, it would be ethyne and then propyne, butyne. Once you get to butyne, though, you have to start numbering because butyne can be terminal or in the middle. So 1-butyne, 2-butyne, and then pentyne, and so on and so forth. When you start having branching as well as the triple bond, then you have to give preference to the triple bond and you start numbering where the triple bond is. Okay, so that's what this nomenclature is. The new one given over here is where the number has shifted to just before this suffix. Okay, it's pretty much the same as far as the substituent is concerned. It's only about the functional group. Okay, that has changed. If you have an alkene and an alkyne in the same compound, then you start numbering from an alkene, but you will end the name in alkyne. Okay, it's a little confusing, I know, but that's what it is. Okay, that's the nomenclature system. All right, so if you have an alkene and an alkyne, then remember the alkene will get the preference for numbering, but the alkyne will get preference for the suffix. Okay, if you have an alkene and an alkyne, in which case the alkene is in the middle, whereas the alkyne is terminal, then the alkyne will get preference both ways, which means that the alkyne you'll start numbering also, and that will also get the suffix. It was getting the suffix before also, but now it will also get the numbering preference. So you can see it's a very small difference between alkenes and alkynes. And it's only a problem when you have both an alkene and an alkyne as terminal groups. But if the alkyne is terminal, then it will get preference. If alkene was terminal and alkyne was in the middle, then alkene would get preference. Okay, so whatever gets the lower number is what gets preference. Again, the new nomenclature is also given over here for you to see, and don't know where you will encounter it, if exams have started using it or not, but it's there, okay, for you to use. These groups over here that are given to you are just for your general knowledge, as in the butyl group, which is alkane group, -1 hydrogen, the butenyl group, which is coming from an alkene, okay, and the branching is right off the double bond, not on the other side. And then the butynyl group, which is coming from an alkyne then, okay, and so these are all substituents that are used, and sometimes these names are also used for nomenclature system, okay, but usually we don't get that complicated with naming for alkynes. We'll keep it simple. The physical properties and applications of alkynes. The physical properties are very similar to alkenes, okay, and so it's not that different. So alkenes, alkanes, alkynes, all hydrocarbons, they behave the same way, which means that the smaller molecular weight alkynes are going to be gases, and as they get heavier and heavier, they become liquid, okay, because the intermolecular forces, which is the van der Waals force or London forces, they increase, and therefore they become liquids, okay, at the end, or as they progress with the molecular weight. And then almost all alkynes are going to be insoluble in water, and especially as they become bigger and bigger in size, then the non-polarity increases, and therefore they're insoluble in water. As far as the applications are concerned, there are very few applications for alkynes as in alkynes. Okay, they're used for other things, but not as alkyne. All right, so for example, the best application that I can tell you for an alkyne is in the acetylene torch. Acetylene is another name for ethyne, and the acetylene torch is used for welding. Okay, it gives a really high temperature flame, and so it's really very good for welding metals, okay, and all that. So that's the only application that I can think of to tell you, because all the other applications include taking the alkyne and using it as a starting material for alkenes or alkanes. Okay, and so it's not really an application as in a direct application, but of course it is still used. Sometimes you may find the alkyne in certain molecules, for example, in some drugs or some hormones, but again, not very common. The synthesis of alkynes is one kind. There are two kinds actually. The first one is elimination, just like for alkenes. Okay, and so this is really the best way to make an alkyne. And again, elimination is going to be when you have a leaving group on it. Okay, and the leaving groups are going to be bromines or chlorines. All right, and so if you have this particular starting material, that's fine. But otherwise, typically what happens is that to synthesize an alkene, you start from an alkene. Okay, to make an alkyne, you have to start from an alkene, you have to halogenate it, and then once you've halogenated it, then you do 2 eliminations on it to get the alkyne. Okay, so that's really is the best way to make an alkyne. So here is another example where you have a straight chain. So you add bromine, again you add the bromine on adjacent carbons, which means it's a vicinal addition. And then you do 2 eliminations. Okay, so one elimination gives you an alkene. The second elimination will give you an alkyne. The only thing about here is that you want to make sure that at the end you protonate this alkyne. Okay, this ion over here has to be protonated, and so sometimes you might see ammonium chloride, which is a weak acid, and you might see that to protonate this alkyne. Okay, but in general what you will see is an alkene that is getting brominated, and then you will see 2NaNH2, which is sodium amide, and in some cases 3 sodium amides followed by 1 ammonium chloride to give the alkyne. Okay, and so this is how we synthesize alkynes. This is one way of making it using elimination. The second synthesis of alkynes is not really a true synthesis. Okay, it's called a chain elongation, which means you're already starting with an alkyne. So you're not really synthesizing the functional group. Okay, you're only doing chain elongation. And so what you do is you start with an alkyne and you extend the chain. Okay, and this can be done only when the alkyne is terminal. You cannot do it if it's an internal alkyne. So what's going on over here? So here is the terminal alkyne, which means there's a hydrogen over here. You treat that with sodium amide. Now remember, this is an acid-base reaction. Alkynes are slightly acidic. So this is an acid-base reaction. So once you take away this proton over here, this has now become a conjugate base. This conjugate base is also a good nucleophile. And this nucleophile will now react with this substrate over here, like methyl iodide, for example, and then you can do a simple SN2 reaction in order to get the product. So all you have done is actually elongated the chain. You have not really synthesized the triple bond, but that's fine. This is still a synthesis of alkyne, okay, in a way. So a little bit review over here for the acid-base strength is that alkynes are quite acidic in nature. The pKa is much smaller than alkenes, which is then much smaller than alkenes. So alkenes really are not even acidic at all, okay, whereas alkynes are quite acidic. And again, if you remember, the reason for it is because once you remove this hydrogen from here and there is an extra pair of electrons, these electrons can delocalize over the triple bond, okay, and so it kind of stabilizes the charge. That charge cannot be stabilized so much on alkene and absolutely not on the alkane, because there are no pi bonds, okay, on this one. So that's how the alkynes are very good acids, and that's the reason why we can use this particular synthesis to make to extend the chain. Okay, the one thing you have to remember here is that you can only use a strong base like an amide to form the ion, okay, the alkanide ion. And this has to do with the acid-base reaction and the fact that the conjugate base that you end up forming here should be stronger than the base over here, okay, and so should be weaker than the bases that you started with. So if the conjugate base that you form here is stronger, then this reaction is not going to happen. Okay, so the conjugate base that you're forming for both should be weaker. The conjugate acids and bases on the product side should be weaker. And so the only base that is possible for this kind of a reaction is the amide. Okay, so using it as sodium amide or potassium amide, this is the only base possible to abstract this proton and make sure this reaction goes forward. So once you've created the alkanide ion, that can now react as a nucleophile. But in this slide and the next one, we will talk about just a little bit about how this ion is used. Because remember, once you've generated a nucleophile, that nucleophile is going to be reacting with the substrate. So depending on what kind of a substrate you have, you can have a nucleophilic substitution or you can have elimination. Okay, so remember all those different conditions that we talked about, having a strong nucleophile, steric hindrance, and all of that that comes into play. So in this case, you have a nice long nucleophile, but you also have a very unhindered substrate, which is a primary substrate. So in this case, you will end up getting substitution. Okay, very nicely, no problems at all. In this case, you have a terminal alkyne, so you get the one substitution. These two examples over here, these are for continuation. So for example, if you start with acetylene or ethine, then you can treat it with sodium amide to give you the conjugate base. This nucleophile now can react with any substrate to then give you this product. Okay, and this product, it still has one acidic proton. So now you can take this alkyne that you just made, and that's the R group, okay, that we have on this side. You can take that one and continue on the reaction on the other side using the other proton. Now remember, you can't abstract both the protons at the same time because you can't have two negatives on one compound at the same time. All right, so you can do this a step at a time. So you substitute one hydrogen, okay, at one time, and then you take the product of that and you remove the second acidic hydrogen and then treat that with another substrate to get this kind of an internal alkyne then. Okay, and so one step at a time. Now let's come back to what kind of a substrate you have. Here the substrate was a primary substrate, no problem. However, if your alkyne is a nice small base or even a larger one for that matter, but your substrate is a secondary halide or a tertiary halide, then we start having issues. Okay, and especially for secondary halides, then you will not get substitution anymore. You will actually start getting elimination. We did this in our SN1, SN2 reactions also, in substitution and elimination reactions. But again, this is just a review. Okay, then that don't forget that just because you want to make this product does not mean you will get it. Okay, because this reaction, whether you like it or not, is going to give you more of elimination than substitution because of the steric hindrance of the leaving group. Now for the reaction of alkynes, most of the reactions will be similar to alkenes, which means they're just addition reactions. But since alkynes have twice the hydrogen deficiency index, which means they have twice the unsaturation of alkenes, they will actually add on twice as much as alkenes will. So if alkenes were absorbing or reacting with only 1 mole of bromine, alkynes will react with 2 moles of bromine. Okay, so that's how the unsaturation works for alkynes. Alkynes are also more oxidized than alkenes, okay, because alkynes have less number of hydrogens. Alkenes have more hydrogens, so they're more reduced. So what happens then is some of the reactions that we'll do with oxidations and reductions is that alkenes may end up giving alcohols, but alkynes will give us aldehydes. Okay, and remember we did about 3 or 4 reactions where alkenes gave alcohols. So those are the two major differences that we have for alkenes and alkynes. But other than that, most of the reactions will be the same, which means that we will add hydrogen halides, okay, which is hydrohalogenation. We'll do halogenation, hydration, hydrogenation, all of these typical addition reactions that we did for alkenes, we will also do for alkynes, and then we'll also do the oxidative cleavage. So the first reaction then is the addition of HX or hydrohalogenation. The reaction works the same way as it did for alkenes, which means that it is a Markovnikov addition, which means that the hydrogen goes to the carbon with more hydrogen. So which means if you have a terminal alkyne, then the hydrogen will go to the carbon with more hydrogen. If you have an internal alkyne, then it's not going to matter because internal alkynes, they have the same number of hydrogens on either side, which is actually 0, okay, because they don't have any hydrogens, they have carbons on either side. So in any case, if you take an alkyne and treat it with HBr, hydrobromic acid, then the hydrogen will go to the carbon with more hydrogen. You get the bromine here, add another hydrogen, another hydrogen bromide, and you get the bromines again on the same carbon now, and the hydrogen will still go to the carbon with more hydrogen. Now the bromine that we ended up getting here is a geminal bromine, okay, because remember we talked about vicinal and geminal. Geminal means on the same carbon. So this is a geminal bromine now, okay, 2,2-dibromohexane. So if you wanted to make anti-Markovnikov products, so for example, if you wanted the bromine or the hydrogen to go to the carbon with less hydrogen, then you would use peroxide. As I said to you when we were doing alkenes, is that whenever you see peroxides, the addition is usually going to be anti-Markovnikov. Okay, so you can do that with this also. Typically, it's not done this way, but still, okay, if you wanted to make the anti-Markovnikov addition for alkynes, you can use peroxides and do the addition. Addition of halogen is very straightforward, no big deal there. So you add one molecule of bromine, okay, to alkyne, and you add bromine to the opposite sides, just like you would have the mechanism for alkene. Remember, going to the bromonium, which means the bromine is adding on to the opposite sides, okay, anti-addition. And then you add another molecule of bromine, and then you add another molecule of bromine to the double bond, okay? And again, it's going to be anti, but it doesn't really matter because if you end up with 4 bromines, you really have no chiral center or no stereo center whatsoever, so it doesn't matter, okay? And typically, this reaction is not stopped in the middle. If you want to do bromination of alkynes, you will go all the way through to give the tetrabromo product. Okay, you will generally not stop in the middle. If you have to stop in the middle, you really have to monitor the bromination very carefully. Okay, otherwise just add excess of bromine or chlorine and then end up getting the tetrabromo product. Okay, complete addition, saturation of the alkyne. Addition of water. The addition of water to alkynes is not as simple as it was for alkenes. In alkenes, we just added water in presence of an acid. Now, in this case, you not only need acid, you also need another reagent. Okay, in this case, mercury sulfate. If you remember, we did 3 different kinds of hydrations. One was with water in acid, the other one was oxymercuration, and the third one was the hydroboration. So we don't do the first one here, we do the second 2 over here, which means that they're using the mercury reagent and then using the hydroboration. Okay, and so the mercury reagent will give you the Markovnikov product, and the hydroboration with hydrogen peroxide will give you the anti-Markovnikov product. Again, this is only when you have a terminal alkyne. If you have an internal alkyne, the Markovnikovs does not matter at all, okay, because then you have symmetrical triple bond. So if you have a terminal alkyne and you treat that with mercury sulfate, you will get the typical Markovnikov addition, which means that the hydrogen will go to the carbon with more hydrogen and you end up getting a ketone. This is another thing that is different from alkenes, because in alkenes, when you added water, you got alcohols. Now, since alkynes are more oxidized, you're getting the more oxidized product, which is a ketone. Okay, so taking a terminal alkyne and you treat that with the borane reagent. So this, if you do hydroboration on this one, now you will get the anti-Markovnikov product, which is the aldehyde. Okay, and so aldehydes are terminal groups. So you end up getting the carbonyl on the terminal carbon, whereas the carbonyl traditionally, if it was a Markovnikov addition, would be on the internal carbon because the hydrogen will go on to the carbon with more hydrogen. Okay, so now the hydrogen is going to the carbon with less hydrogen. Okay, so you have now a choice of making a ketone or an aldehyde depending on your alkyne. Again, don't forget, if you have an internal alkyne, you can use either of these reagents and you will always get a ketone. You will never get an aldehyde, okay? You can get an aldehyde only from a terminal alkyne. So here are a couple more reactions that you can look at, but again, these are terminal alkynes and these are different reagents which are giving you then the ketone and the aldehyde. Reduction now, and again, this is an addition reaction. So alkenes will add on 1 molecule of hydrogen, whereas alkynes will add on 2 molecules of hydrogen, all right, because they have twice the unsaturation. The mechanism is the same, okay, and if you're using hydrogen, then you have to use the heavy metal. So again, palladium, platinum, nickel, any of those are used. And again, this is not one of those reactions, if you're using simply hydrogen, that you will stop in the middle, okay? So for example, you will use excess of hydrogen to start from an alkyne and go all the way to an alkane. All right. Now here, even if you have a syn addition, it's not going to matter because eventually you'll get to an alkane which does not have any stereochemistry, okay, whatsoever. So in case you're not worried about what kind of an alkane you're getting, or that you're getting an alkane for that matter, you can take an alkyne, treat that with excess of hydrogen in presence of a catalyst, and get an alkane. However, if you want to get an alkene from an alkyne, which you can, then you can stop the reaction in the middle. And you have very specific reagents that you can use for this. So the nice thing about the reduction part here is that you can try to make cis and trans alkenes. Okay, so not only are you going from an alkyne to an alkene, you're also able to make cis or trans alkenes, okay, depending on the catalyst you use. So for example, the first one that we have here is a syn addition. So taking a 4-octane, which is an internal alkyne, and you treat that with hydrogen using Lindlar's catalyst. Lindlar's catalyst is palladium on calcium carbonate. So if you use this very specific reagent, then you will get cis octene, and you can actually stop the reaction here if you want to. Okay, this is a slow reaction and this can be stopped right here. You don't have to go forward with more hydrogen. You can if you wanted to, okay, but then you don't need to use this reagent. You can just use hydrogenation with palladium. All right, but if you want to stop at the alkene and specifically make the cis alkene, this is the reagent you would use. However, if you wanted to make trans alkenes, then you would use lithium in presence of ammonia, or you can use sodium or potassium, any of the alkali metals with a base. Okay, and the base that's used here is usually ammonia or any kind of an amine. And so if you take an alkyne now and treat that with these reagents, you end up getting a trans alkene. All right, and then again you can stop the reaction right here. You don't have to go all the way to an alkane. Again, these two reactions here are very useful for making very specific alkenes. Now for the oxidative cleavage, again remember that alkynes are more oxidized than alkenes. So the two reagents that we used before also were ozone and potassium permanganate, which is what we're going to use here as well. So if you use potassium permanganate or ozone, it doesn't really matter. If you have an internal alkyne, they will both give you acids. And again, this is because alkynes are more oxidized than alkenes. So whereas alkenes will give you aldehydes, okay, if you had hydrogens over here, alkynes will always give you acids, no matter what you use, potassium permanganate or ozone, it doesn't really matter. If you have a terminal alkyne, then you will get the acid as usual, but then you'll also get carbon dioxide. And if you remember, the difference between this reaction and the alkene reaction is that if you had a terminal alkene, ozone will give you different products and potassium permanganate will give you different products. Okay, potassium permanganate was a stronger oxidizing agent, and that's the one that gave you carbon dioxide. But here, because alkyne is more oxidized already, even the ozone is giving carbon dioxide. Okay, so again, these little things you have to keep in mind when you're trying to do these reactions. Just a little bit about the qualitative analysis of alkynes. Since alkynes are very similar to reactions in alkenes, it's really very hard to distinguish, okay, between them. The two qual tests that we use for alkenes are also used for alkynes, which is the decolorization of bromine and the precipitation of manganese dioxide. Okay, the only difference between the two alkenes and alkynes is that alkynes have twice the hydrogen deficiency index. And if they are more unsaturated than alkenes, then they will take twice the amount of the reagent, which means that if you were to react the alkyne with bromine, it will add on twice the amount of bromine as an alkene would. So you will have to do a qualitative as well as a quantitative test, which means you just count the number of bromine drops you're adding. And if you're adding twice the number of bromine drops that you would for an alkene, then you have an alkyne. But then how really you really know? Okay, because you have to test an alkene at the same time to see how many drops you're adding for alkene, okay, to figure out for an alkyne, which also is not a very clear test, because if you have two double bonds in there, then they will also take 2 moles of bromine. So really the qualitative test for alkynes is not very clear. Um, you have to do a little bit more analysis, and usually oxidative cleavage is used a little bit more for determining what kind of an alkyne you have. And of course, now that we have all the technology and instruments, we don't really need to do qual analysis for alkynes. Okay, and so, but here are little differences. Okay, in case you come across some of the puzzles of the oxidative cleavage, then you can use this information. So this chapter, yeah, really very short. We have very few reactions of alkynes. Most of them are addition reactions. The halogenation, hydrohalogenation, hydration, and then hydrogenation, and then of course the oxidative cleavage.